Okay, hi everyone. So now that we had a little bit chance to play around and kind of explore functions, we know what a function is and we know some of the terminology surrounding them. It's time to actually get into some formal proofs. So the first thing that we'll do is prove whether or not functions are injective. Remember that injective means one to one. You may recognize this from the slides that I used from the last video. I think this was about page 6. It was kind of near the end. But here's the formal definition of whether or not a function f from a domain x, just some arbitrary set x, to an arbitrary set y, which we'll call the codomain. We'll say f is injective if for every two elements that you could pick, s and t in the domain, this statement is true. We can rewrite this as if f of s equals f of t, then s equals t. So this statement has to be true for any pair of inputs that I pick from the domain. So we'll get to how to actually use this in a proof to prove that a function is injective. First, though, I want to go ahead and make sure we're all caught up to speed. I want to give you a couple more examples of injective functions. We'll not do formal proofs of these, but I just want to ask you, based on the way they look, whether or not these functions are injective. So consider this a little warm-up. So let's start here. Which of the following functions, there are 4 functions here, which ones are injections? Which ones are one-to-one? So I want to make this video relatively short, so maybe pause the video here and try to come up with guesses, and then I'll just get right into the answers. All right, cool, answers. So this first one is not injective. And the reason why, if we would call these two particular elements here, maybe we could call this S and this T. They point to the same place. F maps it to the same place. So f of s equals f of t over here, meaning that the function's mapping both of them to the same element, but s and t are distinct elements from this circle arrow diagram. So the answer is no. Number 2, we can see that any two pair of elements we pick here, they're going to be pointing to different places. So the start of the claim that needs to be true, f of s equals f of t, implies s equals t. This first part is never true unless we have exactly the same element. S and t it refers to exactly the same mathematical object, in which case it obviously would be true. So yes, this would be true. Just a really quick aside, what's the deal with this guy? Nothing is mapping to it. So it's an element of the codomain B that nothing's mapping to. Again, not the subject of this video, but the fact that nothing is mapping to this means that this function P is actually not a surjection, but it is injective. So, okay, moving on to number 3. I purposely just gave you, this is a really complicated piecewise function. To prove this formally would probably be, it's actually not very hard in principle, but we're going to have to rely on some results from analysis, or at least understanding how functions like cosine and exponential functions work. But I kind of made this. The biggest point is, are there any points in the domain, which is all real numbers, whose outputs are the same when those two inputs are distinct? You can see the answer should be no, actually. So any two points we have here, it looks like there's never any time where we're going to have the same y value. Any time we look at any particular y value, there's no other input that gives us that same y value. So we didn't explicitly talk about this before, but some of you may be familiar with the phrase horizontal line test. There's the vertical line test that says whether or not it's a function at all. Things like this are not a function because we've got an x value that's supposed to be giving us two different y values, and that's illegal for a function. But so the vertical line test would say that this isn't a function. This is a function. It does pass the vertical line test, but the horizontal line test gives an indication on whether or not the function is injective. Is it one-to-one or not? So this does pass the horizontal line test. Notice that this is an asymptote. And again, that's our understanding of exponential functions, that it's going to get really, really, really close to this, despite my drawing skills, without ever actually reaching that point of 4, the y value of 4. But things will get very, very, very close to that. But all of these will be be distinct y values for the different x value. And again, so to prove that, maybe we need to understand something about this function in particular. This is probably doing a formal proof of a function like this is just a little bit beyond our goals for this class. Not that it's hard, it's just going to be kind of consuming. It would be a lot faster if we understood things from analysis. Just looking ahead, not for this class, but for future classes, you could make an argument that because this is a monotone decreasing function that's always greater than 4, and it's actually strictly monotonically decreasing, all of these values will be distinct. And of course, they're separate from these other two parts of the piecewise function. Again, the explanation there is completely, do not worry about that for this class, but just in case you remember any of that from calculus, or you happen to be taking analysis, or at least know a little bit of analysis, that's kind of the logic that you would use. Okay, anyway, number 4 is not. Oh, wait, so yes, this is a complicated but still injective function. Number 4, no, and going off our observations for number 3, it fails the horizontal line test. So we could pick a function here, or sorry, we could pick an input here, maybe when x equals 0, and then there's another one here. I'm not exactly sure what that would be, but I don't know. Let's just say whatever it is, alpha. And when x equals alpha, the particular constant alpha, we would have, I'm calling the function g. We're allowed to name our functions whatever. F is just the, classic choice, but we can name it g, we can name it h, we can name it p, doesn't matter. You can even name it x, just make sure that x doesn't mean something else in the context. G of alpha equals g of 0, but alpha does not equal 0. So that would actually be a counterexample. We could explicitly give an example of when the definition of injectivity fails. Okay. So going on from there, let's do a formal proof. So let's start with, I'll call this example 0, and I'll try to make it very, very simple. Let's take a function f that maps the natural numbers to the natural numbers with n mapping to n plus 2. So remember, this showed up on the previous slide, but this particular symbol here means maps to, and it's absolutely equivalent to writing f of n equals n plus 2. I just want to get you familiar with both of the ways of communicating that. So these two statements are completely equivalent. Okay. Anyway, So this should be an injection. You can imagine that any two different values, well, it's always going to map the two above it. So if I have any two values here in the, maybe, okay, why don't I just draw it? So we'll call this the idea. Always a good idea to kind of sketch out our proofs first. But we can imagine, even though it's an infinite set, we can still kind of picture this mentally as a circle box diagram. And you can see I spent way more time on the previous slide before. This is me trying to do it quickly. If we have a function, or if we have an input s and an input t, it's always going to send it down the line. T is going to send it down the line by 2. So it doesn't seem that t is ever going to have, like, if t is greater than s, then it doesn't really make sense that somehow t could go back and meet up with where s is getting mapped to. So this is what we would expect. I'm just trying to communicate using mathematical language what our intuition here is. We don't necessarily have to we don't have to necessarily understand we don't have to necessarily use this sort of language in our proof. It's actually going to be simpler than that. But we should at least understand kind of why we believe this is true. It's not usually wise to go directly into a proof without at least kind of investigating and understanding why it's true. Sometimes that's all you can do because you just don't have a lot of intuition and you can just use the definition and just see if it works. But it's always best to kind of play around with it a little bit before you launch into the formal proof. But just recall, so this was a little bit earlier in the video, or if you've got that definition written down somewhere, if you're taking notes, which of course I do recommend. F is injective means that for all choices S and T in the domain, which here is all natural numbers, if the outputs associated with S and T are equal, then S has to equal T. So that's the definition that we're going to be using. So how do we prove this? Well, pick 2 and then show that this is true. If our choice is arbitrary, then it like, meaning we're not saying anything in particular about the S's and T, the S and T that we pick. If we can show that this always needs to be true no matter what S and T we pick, then we've proved it's injective. So start out. Take 2 arbitrary elements of the domain, S and T. Then the function tells us what to do with them, what their outputs are going to look like. Add 2. F of t means take t and add 2. So what we're going to do now is we want to show that this statement is true. So suppose f of s equals f of t. Then that means s plus 2 equals t plus 2. And now we just have 2 natural numbers, and we understand how operations with natural numbers work. Or, you know, they're a subset of the real numbers. We understand how operations involving real numbers work. We don't have to pretend like we don't. So we're allowed to, if these 2 numbers are equal, we're allowed to simply subtract 2 from both sides. That implies that s equals, not 2, sorry, s equals t by subtracting 2 from both sides. So supposing that the outputs are equal, we've simply applied the definition of the function, and we've arrived at our conclusion that s equals t. So f of s, and all that's really left is just to, again, because we're trying to kind of, we're not very familiar with this. It's always good to say a little bit more than you need to say. Don't leave the reader hanging and expect them to necessarily follow along with your argument perfectly. It's nice to just offer them a conclusion. So f of s equals f of t implies s equals t. And then you could say, since our choice of s and t was completely arbitrary, we didn't have any specifications about what they are other than that they were elements of the domain. F is injective. And that's it. So, moving right along, I want to maybe look at a more complicated function now. So let's take this. We'll call it f again, whatever. And this one will be a little bit more involved, but that's okay. So here's our job. Prove the function f from the natural numbers to z given by make this a little bit tinier. F of n equals, go ahead and make it a piecewise function, n divided by 2 if n is even, and negative n plus 1 divided by 2 if n is odd. Okay, so this is a particularly interesting function. I'll use this one in the next video too, but this is a piecewise function. Before we get started proving, before we get started, let me finish my sentence, is an injection. So before we get started, do want to say this. We should, because this is a little bit complicated, we should prove that this function is actually well-defined. And by well-defined, I mean it is a function. Or even if we don't have a formal proof, we should at least convince ourselves that it's well-defined. Does it make sense? No matter what element of the domain we're given, is there one unambiguous output that that element of the domain is mapped to? Or is this function, are there some elements of the domain where we could, maybe like both of these would apply? Moreover, are these operations, if n is a natural number, can we always divide by 2 here? It's an important thing to do, and I promise that when you take future classes, you will, for example, abstract algebra, you will prove functions are injections. You will sometimes get complicated functions using mathematical, or functions that are defined in ways that seem a little confusing. It might be a little hard to wrap your head around, and you should not take for granted that they're functions. Or maybe you're trying to create a function, and you want to make sure that it's a function before, because you can't, if you prove something's injective, but it's not even a function. You haven't really proved it's injective, right? So go ahead and call this step 0, I guess. F is well defined. Do need to start there. Let's at least convince ourselves. We don't have to make a formal argument here, but let's at least convince ourselves. So any element of the domain that we have, is there any chance that both of these statements could be true? No, right? A natural number is either going to be even or odd, and there aren't any natural numbers that are in neither group. So no matter what, in exactly one of these will apply. So that's good. And second of all, if it's even, we know that there's a factor of 2. It's going to be of the form n equals 2k for some integer k. I mean, in this case, it'll be a natural number, but n will be n will have a factor of 2. So yeah, we can divide by 2. So that operation makes sense. We're not going to get something that we're not going to be able to do. If it's odd, we're going to have something of the form. So n is odd. We would have something of the form 2k plus 1. So does this operation make sense? Are we necessarily going to get something in our codomain, or are we going to fall outside, or are we going to have to do some operation that doesn't make sense? So it's good to check. If n is 2k plus 1 divided by 2, that would give us 2k plus 2. Divided by 2, and of course that would simplify to negative k minus 1. So that would be an element of our codomain. So yeah, it is nice. This function is doing what it's promised. We're starting with, sorry, it's really loud. We are starting with elements of our domain, and we are getting guaranteed elements in our codomain. We're not so this function is defined for all elements of the domain, and it is sending all of them to the codomain. So yeah, it is a function. It is well defined. So now with that out of the way, we haven't necessarily explicitly talked about that yet, except for just kind of like looking at circular arrow diagrams or maybe vertical line test. But that is the kind of argument you'll have to make to prove that a function is well defined. Okay, so in order to do this, let's just go ahead and, I guess, just to try to keep this video relatively short, let's just kind of tread right along the line here. Let's start with 2 arbitrary elements of the domain. We'll do the same proof. Take S and T, or same proof strategy, I mean. Take 2 elements of the domain, completely arbitrary. And we want to show that if their outputs are equal, then S equals T, or their inputs are equal. So let's suppose that this first part's true. We want to show that the second part is directly true as a result. So what's next? Well, it's a little weird because we don't exactly know what this function is supposed to do with S and T, right? It depends. It depends. Is S even? Is T even? Is S odd? Is T odd? What we'll have to do, you guessed it, we'll have to do a case-by-case proof. We don't know anything. These are totally arbitrary. So we have to just simply cover all the cases that could possibly work. Oh, I did not like whatever that was. Bad. Okay, I'm at 5,000% zoom. Okay, we're good now. So, case 1. Suppose S and T are both even. And then going forward, we would say suppose they're both odd. Case 3 would be we want to cover everything. And then case 4 would be suppose T is even and S is odd. I don't really need to do all these for the video. Let's do the hard ones. Let's do a few of them, or at least start what it would look like. So let's see. Looking at here, go ahead and say case 1. Suppose S and T are both even. We already know that they're natural numbers, but we want to prove that since we're already assuming that f of s equals f of t, and we know that they're even numbers, we do in fact know what these things equal algebraically. That would mean, so I'll try to form this. This statement would imply, again, we know what the function does because we understand it's a well-defined function. This is the only thing that can happen to S and T being even inputs. And again, we understand operations involving, standard real numbers. We can multiply both sides by 2 and still get an equivalent equality. S equals T, so check. So in case 1, we get evidence supporting that f is an injective function. Case 2, suppose they're both odd. And again, this would imply that here's the unambiguous thing that happens. Using our value of s for their input here. So f of s equals f of t would mean that these two numbers are equal. Do standard operations, multiply both sides by 2, multiply both sides by -1, subtract 1 from both sides, and we end up with s equals t again. Cool. So what's next? Case 3. So maybe just here I'll say in the case where they're both even, just a little summary here because I'm kind of working one slide at a time. If they're both odd, this statement. Let's look at case 3 now. And case 4 will be very similar to this, so might as well just do one of them. Suppose s is odd and t is even. And of course, we are assuming from before we are already assuming that f of s equals f of t. That would imply well, s is the odd one, so t is the even one. So here's what f does to even inputs, and here's what f does to odd inputs. So we get this statement, which of course implies now we have a problem. What's wrong with this statement? So what's wrong with it is that t is a natural number, which means, of course, t is greater than 1. Greater than or equal to 1. Might as well just, okay, greater than 0. That's what I meant to say. So t is greater than 0, but s is greater than 0, so s plus 1 is greater than 1, which means negative s plus 1 is going to be, it's going to be less than negative 1. So we've got t being a positive number equaling to a negative number. This is a contradiction. What does that mean? So we remember, just recalling from last unit, if we have a contradiction, what that means is we made an assumption somewhere that wasn't valid. So we simply have to retrace our steps and say, okay, well, what could we possibly have done that introduced this error in the logic? It's not really an error, but this falsehood in our proof. And going back, this all seems fine. That's just how inequalities work. This was the very first thing that we said in the proof. Again, that's just what it means for for operations of real numbers. That's just the definition of the function. So going back, it should be that. So that was an assumption that we made, because we're just going through all the cases and saying, here's all the different things that S and T might possibly be. But the problem is, this will never happen. Since we assumed, first of all, that was true, then we said, okay, well, let's go through the cases and say what S and T could be. This one is impossible. So f of s will never equal f of t when this statement's true. So again, this doesn't mean that our proof for injectivity fails. It just means case 3 is not possible. And then if you do case 4, it's also impossible. Meaning it's our assumption that s is odd and t is even, and then here our assumption that s is even and t is odd. Both of those are incorrect assumptions. So, wrapping up, we're basically done with our proof. We handled all 4 possible cases here. and based on all the different things S and T could be, because remember, S and T were completely arbitrary. We didn't know anything about them, and we just said, okay, well, here's all the different here's the different things that could happen depending on what S and T turn out to be, what our particular choice would be. In all the cases, case 1 and case 2 leads to the result of injectivity, and case 3 and case 4 simply can't occur with the assumption that the outputs are equal. So, wrapping up, we'll say, so for all S and T in natural numbers, that implies S equal T. So that's the definition of injectivity. So therefore, F is injective. I was briefly talking about what this function meant briefly talking about what this function meant at the end of last lecture, or last class meeting, I should say. They're not really lectures anymore. This is, it didn't explicitly say what it was, but if you watch the video, you might have an idea, because I talked about it in one of the groups. But we will talk about this probably not on Tuesday, but on Thursday. Very, very cool function. Says something pretty great. But this function, starting with the domain of natural numbers, going all the way to integers, that is injective. As a really quick aside, is it the only injective function from the natural numbers to Z? Of course not. That is the end of our proof, but just as an observation, another choice of an injective function, maybe we'll call it G from N to Z. Since this is a subset, the natural numbers are a subset of the integers. G of N equals N is also going to be an injective function, and it's going to be, the proof of that is basically one line. So I invite you to use the language that we did in the previous two proofs to prove that is injective. But it is very, very easy to see that is an injective function. However, G is not going to be a surjective function because N is always going to be a positive number, and Z contains negative numbers too, so there's no way that we're going to get anything that maps to negative elements of the codomain. This one, however, is surjective. It's very interesting. We've got a function that has a domain and a codomain where the size of this, if you think about it, or you should at least say all of the elements here are contained in Z. The domain is a subset of the codomain, and yet this function is both injective and surjective. So it covers everything, and all of the outputs are unique to their inputs. Or they're unique across all inputs, I should say. Very interesting. What would that mean?